Torque practice problem number 1. Suppose we apply a perpendicular force of 80 newtons to a door at a distance of 25 centimeters from the hinge. How much torque is applied? So if it's helpful to see, here would be the hinge about which the door could pivot. And let's say I put this 80 newtons of force. 80 newtons. It is a distance of 25 centimeters, so we need to convert this to meters. You divide by 100. So 0.25 meters, and it is perpendicular. How much torque is applied? Torque is equal to F cross R. In this case, the angle between the pivot and my force applied is 90 degrees. So this is just F times sine of 90, which is 1, times R. So 80 times 0.25 meters, 80 newtons, times 0.25 meters, that's 80 divided by 4, which is 20 Newton meters. And do not confuse this with joules. This is a torque unit. Okay, problem number 2 up next. Practice problem number 2. A 5 kilogram mass and a 3 kilogram mass are placed on top of a seesaw. The 5 kg mass is 2 meters from the fulcrum. The fulcrum is this triangular piece right there. Okay, as shown. Where should the 3 kilogram mass be placed in order to keep the system from rotating? So to keep the system from rotating, the torque on the left, or the 3 kilogram torque left, needs to equal the torque on the right. Okay, when that happens, the system is in rotational equilibrium. So we will say that torque is R cross F for the left side. We're looking for R, and the force applied on the left side is the weight of the object, 3 kilograms times, I'm going to use gravitational acceleration of 10. So 3 kilograms times 10 meters per second squared gives me an applied force of 30 newtons on the left side. And for the object to not rotate, this left side torque needs to equal the torque on the right. So same thing, we have the torque on the right side is due to the 5 kilogram mass, or the 50 Newton weight at a distance of 2 meters from the fulcrum. 2 meters times 50 newtons. And this way we can find where this 3 kilogram mass should be placed. So R equals 2 times 50 is 100 newtons times meters on top, divided by 30 newtons on the bottom. The newtons will cancel. And so R should be placed a distance of 100 divided by 30, which is 10 over 3, which is around 3.3 meters. Next up, problem number 3. Practice 3. The Discobots are designing levers for their robots. The V5 smart motor will allow the arm to rotate around it. This motor has a stall torque of 1.5 Newton meters. If the students are trying to maximize the amount of load on the arm, what are some things they should consider? So just so you know, the motor works right here where I'm circling, and it acts to spin this belt, which will eventually rotate this. Either direction, you can lift this thing up. If it rotates this way, you can crank it down. If it rotates clockwise direction, counterclockwise will lift. So some things to consider pertain to the stall torque. The stall torque is when the motor can no longer overcome the amount of torque needed to rotate. Stall torque is the torque, it's the maximum output torque of the engine. So you're going to answer this question yourself, and I want you to think about some things you would need to consider, or the Discobots need to consider, if they're designing this lever. They know their engine has a maximum output torque of 1.5 Newton meters. What are some things you need to consider when analyzing torque? Okay, think on that. Follow me to practice problem number 4. Practice number 4, a force of 450 newtons, please omit this redundancy, A force of 450 newtons rests on a 0.3 meter long rotating lever. How much torque is applied to the lever? Okay, so the first thing you should know is that torque acts on this lever because of this weight. This weight vector is 450 newtons. And it's really important to get this concept. Only force that is perpendicular to the moment arm or to the lever arm applies torque. That's the key to cracking problems like this, where you have non-perpendicular forces acting to rotate. So even though we have this 450 newtons of force going straight down, because this lever arm is rotated at an angle of 50 degrees above the horizontal, only part of this weight vector acts to cause the rotation. So to see that, I'm going to extend the moment arm vector all the way up. This is the vector along which a force can act to cause rotation about this circular piece right here. So this vector, the R vector, the moment arm or lever arm, forms an angle of 40 degrees between the weight and itself. So there's an angle of 40 degrees between the weight vector and the R, the moment arm vector. I know this because this is like a right triangle. 50 degrees plus 90 degrees plus 40 degrees, all of that sums to be 180. A right triangle has angles that sum to 180 degrees. This will help me draw my vector components. It will help me figure out what component of the weight gives rise to torque. So I'm going to split this weight vector up now into its perpendicular and its horizontal vector, but I'm just going to look at the perpendicular vector for the weight. So this is the component of the weight that is actually perpendicular to the arm, to the R or the lever arm vector. And this angle in here is the angle that I'm going to look at because I need to figure out what the magnitude of this green vector is. So once again, I have a hypotenuse, which is the weight. I have this side that's adjacent to the angle here, and can you see that if this is totally perpendicular, if this green vector is totally perpendicular to the moment arm, then it forms part of 90 degrees. I have 40 degrees here, which means that the angle, this blue angle, is 50 degrees as well. It's the same as the horizontal angle, or it's the same as the angle the moment arm makes above the horizon. So this green vector is the force that gives rise to any torque. So we'll calculate it. This green vector is a cosine. So the green vector, the W perpendicular is equal to the hypotenuse, which is 450 newtons, times cosine of 50 degrees. So even though we've been talking that R is equal, or torque is equal to R cross F, I have already now done, just using triangles, I've done the cross product. And it turns out in this case the cross product is cosine of 50 degrees. So I will do in my calculator 450 times cosine of 50 degrees. Pardon the sirens, I live right by the fire station. So, and I get that the perpendicular component of weight is 289 newtons. 89 newtons. Now this is the maximum torque applied by the weight. So we can now calculate torque is equal to this 289 newtons times the distance to the lever, or sorry, times the distance to the pivot point, the lever arm distance, length, excuse me. And so torque is equal to times 0.3, 86.776. I'll just round up to 87 newtons times meter. These are more advanced problems. IB will never ask you to this level, at least not that I've seen, but you will see this in college. It's not too bad, you just need to be good with vector analysis. Okay, follow me to question number 5. Practice number 5. A 900 Newton plumber stands at the end of a 0.8 meter long wrench as shown. The wrench makes an angle of 19 degrees above the horizontal. How much torque is applied? So this is a problem I borrowed from my university physics textbook, but you can definitely do it. It's just like the problem before. Notice that the weight and the angle above the horizontal kind of form a right triangle. So if I extend this dashed line, you can see very clearly this is a right triangle. All the angles in a right triangle sum to be 180. So this angle up here has to be 71 degrees. So just like before, you need to split this weight vector into its components. I'll extend the moment arm, which is along this wrench. I extend that R vector. The moment arm is the same thing as the lever arm. And what we can do is, once again, you're going to make your component of the weight that is perpendicular. So this is the component of the force vector that is actually perpendicular to the moment arm. And then, of course, we have our parallel component, but we don't care about the parallel. The parallel force does not apply any torque. And so this angle between the purple vector and the red vector is, it's 19 degrees. So just like before, you are going to calculate the W perpendicular component, and then you'll use this to get the torque applied, where torque will be the W perpendicular times the moment arm length, or the magnitude of the moment arm. Okay, do this one and then meet me for practice problem number 6. Practice number 6. A motor rotates a lever arm as shown below. Which of the positions requires the most torque output from the motor and why? In this case, I want you to consider once again the angles. I want you to draw a free body diagram, and I want you to break this weight vector into its components. I guess you can start by drawing the distance, the length of the moment arm, and then you can translate this weight vector straight onto that. And then I want you to break it into its components, just as we've done before. And I want you to talk about the difference in the angles. So discuss angles and when you have, and then at what angle you have maximum torque. Max tau. Okay, so with that in mind, this is really just a continuation of number 4 and 5. It's just without without actual numbers. This is a conceptual question. So draw your vectors and then just in writing, tell me which one exerts the most torque, or which motor has to use the most torque. Okay, next up, practice number 7. Practice number 7, moment of inertia, everyone's favorite, right? Okay, a rod can be rotated along 3 different axes of rotation. Rank the moments of inertia from least to greatest. Now, I know this isn't a calculus-based physics course. We don't have to derive any of the expressions for the inertial moments, but it's easier to think about it if you realize that the moment of inertia, moment of I, is an object's resistance to a change in rotation. An object's, I'll just say like this, is an object's ease of rotation. So the greater the moment of inertia, the harder it is to get that object rotating. The lower the moment of inertia, the easier it is for the object to rotate. So let's look. If I look at, say, this one right here, you try rolling your pencil around. It rolls really, really easy along its center axis like that. Similarly, it is easy, though not quite as easy, to rotate your pencil like this, about its center. However, rotating your pencil around one end becomes extremely difficult. You can feel it in your fingers as you try to rotate it like that. So based on that, can you rank them in order from the least to the greatest moment of inertia? Next up, practice problem number 8. Practice problem number 8. Find the moment of inertia of the dumbbell about its center. Okay, each end has a mass of 15 kilograms. So it's going to be rotating like this. This is 15 kgs and this is 15 kgs. And assume the 30 centimeter handle is massless. Well, that definitely makes it easy for us. So what we will do to get the total moment of inertia is you will add up the moments, the inertial moments for each end. And this will give you the total moment of inertia for the dumbbell. So unless otherwise given in a problem, you should use the equation that's given in the data booklet, I equals sigma, which is the sum of the masses times r squared, where r is the distance to the axis of rotation. It's the moment arm. Okay, so we will do that. I equals, in this case, they're both equal and they're both spaced 15 centimeters from the axis of rotation, because it said that the handle, the massless handle for our convenience, is 30 centimeters long. So we will do 2 times their masses, 15 kilograms, times 0.15. I've just converted this to meters by dividing by 100. Oops, meters squared. We add this up and we get 0.675 kilogram meters squared. And please note, I squared everything in here. The 0.15, the meters get squared, the 0.15 gets squared. So this is our answer, 0.675 kilogram meter squared. Up next, practice problem 9. This practice problem is great because it shows how it's harder to rotate an object about its end rather than its middle. So let's see. Find the moment of inertia of the dumbbell about one of its ends. Each end has a mass of 15 kgs. Assume the 30 centimeter handle is massless. Again, that's for our convenience, as we'll see with practice number 10. Oh, I'm trying to draw an axis of rotation here, and that did not come out right. So I'm drawing this dashed line here across, and it's going to be rotating about this. So it's going to be arcing around one of its ends. So let's calculate the moment of inertia. Right now, this end right here is a distance of 0 meters from the axis of rotation. So it does not affect the object's moment of inertia. Instead, the only thing that affects the object's moment of inertia is this end right here, this 15 kilogram end. It is not 0 meters from the axis of rotation. It is the full 0.30 meters from the axis of rotation. 0.3 to here. So now we will get the mass. It is 15 kilograms as previously stated, times 0.3 meters squared. And we get, let me pause this. Okay, we get 1.35 kilograms times meters squared. I'm trying to save a little time on the videos with my calculations. Okay, now in practice problem 8, we got the moment of inertia in practice 8 was 0.675, and that was with it rotating about its center. So you can see how, because the length, the distance from the axis of rotation, it's squared, this is squared, it has a bigger effect on an object's resistance to a change in its rotational velocity, or a resistance or an ease of its rotation. Finally, practice problem number 10, the hardest one on here. Okay, so practice number 10. Find the moment of inertia of a rod about its end if it has a solid sphere on the other end. We're given an equation for the moment of inertia of a rod. It's equal to 1/3 ml squared. And we're given the equation for the moment of inertia of a sphere, which is 2/5 mr squared. Now, it's important to note that in truth, we've already been using the parallel axis theorem. The parallel axis theorem is a method of integration. You sum all of the masses acting along an object that is rotating about some axis. You determine how far these massive distributions are from the axis. You add all of them up, and then you get a resulting equation. In this case, that was done for a rod about its end, rotating about its end. So this is the moment of inertia of a rod rotating about its end. The parallel axis theorem has already been used here. The parallel axis theorem will then be applied to our sphere. Okay, so this isn't a calculus-based physics course. So when we determine moments of inertia for objects, all you're doing is adding up. There's no integration. You don't have to look at anything complicated. And this problem would be the most advanced problem you would see in IB. And I'm trying to do this delicately. So what we will do is we will add up the moment of inertia for the rod, which is easy to calculate. And then we need to consider, we will apply the parallel axis theorem to the sphere. PAT, parallel axis theorem, will be applied to the sphere. So we will sum the parallel axis for the sphere to get the total moment of inertia. The moment of inertia for the sphere, using the parallel axis theorem, we will calculate using the Isphere equation, which would just be looking at the object if it was rotating alone by itself about its own center of mass, and then you combine that independent rotational inertia with the fact that it is actually rotating this far away from an axis. So we take the sphere's mass and then we multiply it by how far away it is, this distance d, how far away its center of mass is from the true axis of rotation. And I know this is complicated and I'm really trying to explain this without going into integration, but for this level, all you have to do is you add up all of these moments of inertia. And that's all we're doing. That's all we've been doing for the course, or for the past few practice problems. So we're looking for the total moment of inertia. To get that for this system, we will calculate the moment of inertia for the rod, equation is given. Then we will add that to the total moment of inertia for the sphere, which we calculate by calculating the rotational inertia of a sphere as if it was just rotating by itself about its own center of mass, plus how far away it truly is from the axis of rotation. And notice that these axes, this fake axis that I've created just looking at the sphere, is parallel to the true axis of rotation. That's why this is called the parallel axis theorem. There's also the perpendicular axis theorem, but thank God that's beyond the scope of this course. So I sub p, we're just looking at the spheroid, so I will calculate the moment of inertia of a sphere itself, of this sphere, as if it was just rotating by itself. So we do 2/5 times its mass, labeled 15 kilograms, times its radius, which it has a radius of 1, and 1 squared is just 1, plus its mass, 15 kilograms, times how far away it really is from the axis of rotation. That's 8 for the length of the rod, plus 1 makes 9. 9 squared. So I sub p, I'll simplify this. Let me pause the video so I can calculate. Okay, so I sub p, that's 2 times 15 divided by 5 times 1 plus 15 times 9 squared gives me 1221 kilograms times meters squared. Okay, and now to get the total moment of inertia for this system, I'm going to add it to the moment of inertia of the rod, which is 1/3, times the mass of the rod, 12 kilograms, times its length, which is 8 squared, and this gives me, pause for a moment. Okay, so the moment of inertia of the rod is 256 kilograms meters squared. So I will add 1221 plus 256 up top. One moment. Okay, let me make space up here. We've already calculated. We're now going to get the total moment of inertia. Okay, make some space, make some space. I'll do this in a different color. I total equals 1221 plus 256, and that is equal to 1477 kilograms times meters squared. Whoops. Okay, that's all. Thanks for watching and study well.